Presentation, we're going to focus on proportion tests. The other presentations within the basic statistics realm, introduction to confidence intervals and hypothesis tests, one sample t-test, two sample t-test, paired t-test, have all focused on continuous numerical data, where we take a sample, measure something on a continuous scale, and it makes sense to calculate a mean or standard deviation and then do some sort of t-test approach. Now what we're looking what we're doing is, instead of a continuous scale, we're simply measuring a binary outcome. So something can be recorded as, say, good, bad, defect, no defect, go, no go, pass, fail, reaction, no reaction, something along those lines. So since we're looking at either proportion defective now, because all we're measuring is, you took 100 things and 60 of them happen to have no defects. So then we would, say the proportion of no defects is 60%, or we can talk about proportion defective at 40%. So it really doesn't matter. It depends on how we want to phrase our hypothesis. So if we code the data as zeros and ones, though, notice that if we had 100 data points again, and 60 of them were no defects and 40 were defects, let's suppose we code the 40 defects as ones and the 60 no defects as zeros. If I just take that column of 100 numbers and add them up and divide by 100, I would end up with the 40 ones over 100, which is 0.4, which is identical to the proportion. So mean and proportion in that sense are the same if we code it as 0 and 1. However, it does not make sense to find a standard deviation of those numbers because the coding is arbitrary, and we could have used text, go, no go, or defect, no defect, and we would not even been able to find a standard deviation in that sense, though we could still find a proportion. Okay, so we don't want to find a standard deviation that way. So in general, this type of data follows a binomial distribution. Although it is common to use a normal approximation to solve the problem, it actually follows a binomial distribution, the bi part coming from two possible outcomes. So let's consider an example involving airplanes landing at an airport. So airplanes are required to stay within a certain distance of the runway in terms of left and right. So as they're on their approach to the landing, for safety reasons, they're supposed to stay within a certain plus or minus delta range around that runway. Well, what they do is a lot of times when they deviate this, they call it an exceedance, and they just report you exceeded or they did not exceed as they landed down. So not necessarily the distance from the target or how far outside they were, just either they were outside of that deviation zone or they were not. And a lot of times it's referred to as an exceedance. Historically, a particular airline has 12% exceedance at a medium-sized airport. So we're looking at focusing on one particular airport. And this airline that we're looking at, in general, has had, over the past, a 12% exceedance. Now, while that sounds like a lot, deviating outside of this range is not necessarily like they're going to bump into another airplane, but it is still part of the safety program nonetheless. So the airline embarked on a training program for the pilots who land at this particular airport, who fly planes into this particular airport, to reduce this exceedance. So this particular airport maybe still a lot of crosswinds, or they have to come down over the mountain, or something else that seemed to create a little bit harder landing scenario for the pilots. So they embarked on a training program and went over this to try to reduce this exceedance at this particular airport. So after the program, they went ahead and they collected a random sample of 250 of these landings at the airport, at that airport, and it resulted in 22 that were an exceedance. So we can refer to the sample proportion as p hat from a notational point of view. It is simply referred to a lot of times as x over n, where n is the number of opportunities, in this case 250 of the landings, And X refers to the event that happens, allowing you to define X as either a defect, which in our case is an exceedance, they're outside of the range, or a non-defect, which in our case meaning that they stay within their zone and they do not perform an exceedance. So we're going to define X in terms of exceedance in this case, because that's what our original 12% was in. So notice 22 divided by 250 results in a proportion of about 8.8%. Okay, so a little over 3% reduction from what they were at before to where they're at now. Becomes, well, what do we do with that in terms of a statistical test? So we can state the hypotheses here. A lot of times these hypotheses are written in textbooks or manuals with P's. I'm using theta here to try to stick with the Greek letter notation for parameters. We use mu and sigma are very common symbols to stand for the mean and standard deviation of numerical data. So here I'm using theta instead of p just to make it clear that I am talking about an unknown parameter here. So we're looking at theta equal theta naught versus less than theta naught for our particular example, because the goal of the training program was to reduce the exceedance. So if we plug in our theta naught, which is 12%, we're saying, well, we're equal to 12%, and then what we're trying to see is, well, based on this program that we introduced, did it reduce the exceedance to less than 12%? So theta here is the true proportion of exceedance. So note how these hypotheses resemble one sample t-test, though. I mean, we would have like mu equal mu naught versus mu less than mu naught. So now we just have a theta. So then the terms of the analysis and the way it looks, the way the test statistic looks, the way a confidence interval will look, will fall out very, very similar to a one sample t-test, or more particularly a one sample z, because we'll be using the z distribution instead of the t. Do note that this is a one-sided case because in our particular example, we're trying to reduce the exceedance. However, we could always do a not equal to case or a greater than case. It's not specific. This is just this example. So let's state the test statistic and figure out how we're going to do that. So as I mentioned earlier, the common approach for analyzing this data is to use an approximate method based on the normal distribution. So what we do is we convert everything to a z-test or a normal test, and then we follow along with things that we're familiar with. So our test statistic in general, z again resembles similar to a t. So it's our estimator minus our hypothesized value divided by a standard deviation for the estimator. So that means the top is p hat minus theta 0. Now, under the null hypothesis, we can write sigma p hat, okay, the standard deviation of our estimator. In general, you would write it as some estimate, but we can write it as theta 0, 1 minus theta 0 over n. This is because under the null hypothesis, theta, the unknown theta, is supposed to be theta 0. So under the null hypothesis, instead of using p hat inside the sigma, we're going to use theta 0 because of the null hypothesis. Now, the normal approximation is usually considered adequate if the interval theta 0, okay, which is our null value of 12%, plus or minus 3 times the sigma p hat that we just defined, if that interval is completely contained within 0 and 1. So for our example, that interval is 12% plus or minus 3 times 12 times 88, 12 times 1 minus 12, divided by the 250, and that results in an interval of 0.058 to 0.182, which is completely between 0 and 1. Another common way of saying that is whether n theta 0 is greater than or equal to 5 and n1 minus theta 0 is greater than or equal to 5. So we could also perform that kind of idea. Now notice you really only have to use the lower value. So in our case, theta 0 is much lower than 1 minus theta 0. So we could look at 250 times 0.12, which is plenty bigger than 5, so we don't need to worry about that. Okay, so that's another approach to say, is the normal approximation reasonable? So we do need a large sample size to be able to do that approximation. So what's the critical region? Well, for our particular example, we are looking at a less than case, right? So we're going to reject if z, because we are going to use this normal approximation, so we're going to talk about a z statistic. If z is less than minus z sub alpha, okay, so no different than doing a less than t, where we would have t less than negative t alpha, except we'd have degrees of freedom. Since we're using a z, we don't have that. So z alpha, or minus z alpha in our particular case, comes from the z table. And if we're using a 5%, then minus z of 0.05, you can see the picture, that's the shaded region down there in red, is minus 1.64. So if our z statistic is lower than minus 1.64, then we would reject the null hypothesis. Alternatively, as we mentioned in most of the other presentations, most software packages will present the p-value, which for our particular example would be to find the the z statistic, and look at what is the probability that z is less than that statistic. So that would be in the lower left corner of that, where that test statistic lies. Look at the probability of being less than that. Notice we do not need to multiply it by 2 in this example, because we're looking at the one-sided, just lower-sided case, and so no need to multiply by. So if we conduct the experiment, carry it out, which we've done, we've got the 8.8% sample thing. So the top of our z statistic is going to be the sample statistic, 0.088%, or 0.088, 8.8%, minus 0.12, or 12%. Okay, that's that. Again, the z statistic, I'm not writing it here, but also represents a sort of distance over variation. Okay, the bigger the distance, the more likely something's going on relative to variation. So in the bottom, again, we are using theta 0, because under the null hypothesis, theta is equal to theta 0. So we have the 0.12 times 1 minus 0.12 all over n of 250. So all this boils down to a statistic of minus 1.56. So recall that our critical region is z less than minus 1.64. We could also calculate the p-value. P-value would be putting the 1.56 negative on the z table, on the z curve there, and finding the probability in the left tail from minus 1.56. That probability is a little bit bigger than 5%, almost 6%, 0.0594. So we could also find the p-value. If we wanted an exact test, then we could use the binomial distribution. As I mentioned, that is the true distribution, and directly calculate the p-value without formulating a test statistic per se, of just finding the probability that x is less than or equal to 22, okay, because we saw 22 exceedances, assuming that x is a binomial random variable with n of 250 and theta of 0.12. So if we take a binomial distribution with those parameters, 250 and 0.12 for theta, or p as it's referred to most of the time for binomial, and find what's the probability of observing less than or equal to 22 defects or exceedance. That probability comes out to be 0.0677. So you can see it's reasonably close to the value that comes from the approximate normality one, which is 0.0594. So what will be our conclusion? Well, because minus 0.156 is not less than minus 1.64, or the p-value of 0.0594 is not less than 0.05, or the 0.0677 from the exact test, then we fail to reject. There's not enough evidence to support that the true proportion of airplanes in exceedance is less than the 12% it was before training. So even though it's gone down a little over 3%, statistically it's not far enough to say that the training was really effective. There's some indication from just the value itself, but statistical evidence is not there to prove that the training was effective. Okay, so in this particular one, instead of separating out 1 and 2 proportions, I'm going to do them both together. So now we're going to move on to what if I have 2 proportions that I want to compare together? All right, so suppose we take a random sample from 2 independent populations in which to compare the proportion defective or non-defective. Again, it doesn't matter. So this is similar to a 2-sample t-test. So the 1 proportion is similar to a 1-sample t-test, or more specifically a z. And the 2-proportion test is very similar to a 2-sample t-test, but instead of comparing means, we're comparing proportions. Just like the 2-sample t-test, the sample sizes from each of the populations does not have to be equal, although it is more powerful test if they are, and most software programs will require that equal sample size is taken. Suppose we have 2 industrial plants making the same product, and one of the quality characteristics of interest is whether there's a crack on that particular product. So it's a visual inspection. We're looking for cracks, okay? And if it is, we say, yes, it's cracked, and no, it's not cracked, or pass, fail, whatever we want. So assuming we've standardized the process between the 2 plants so that there wouldn't be anything due to different processes that are going on. And we verified the measurement system so that we know that we can get reasonable answers from people looking at those since it's a visual test. We would like to compare the defective proportion between the 2 plants. So I want to know, is there any difference in proportion of cracks or defects made by plant A versus plant B? So suppose we take a random sample of 200 products from each of the plants. So we go out, we take 200, we inspect them, we get 8 defects from plant A, or cracks, and we get 16 defects from plant B. So we can make sample proportions very similar to what we did for the 1 proportion. We take the number of defects and divide by the number sampled. So 8 over 200 is 4% defective from A, and 16 out of 200, or 8% defective from B. So notice that B has twice as many defects, okay, in terms of twice as big. So the question is there any statistical difference between the 2 plants? Even though it's twice as large, double the amount, 8% versus 4%, we want to know if it's statistically different. So first we state the hypotheses. So again, I'm going to use thetas. Just like a 2-sample t-test, it's going to be theta A equal theta B, or we can use theta A minus theta B equal to 0, so that we could, if we wanted, to form a confidence interval and look for 0. This will be a non-equal to case here because there's no precursor of what plant's supposed to be better. We're just trying to decide if there's any difference between the plants. And also, notice how it does resemble a 2-sample t-test. We're just basically, again, replacing mu's with thetas. Again, the most common approach will assume that the data is using a large enough sample to use a normal approximation. Our estimate of the parameter theta A minus theta B is going to be the difference between the 2 sample proportions. Now this again is analogous to the 2-sample t-test, where the parameter of interest is mu A minus mu B, and we use y bar A minus y bar B as the estimator. So similar idea. Now we have a standard deviation of sigma sub p hat A minus p hat B of exactly what we'd expect. We're replacing each of the thetas there by theta A and 1 minus theta A, and theta B and 1 minus theta B. Okay? So similar to sigma 1 squared over n1 sigma 2 squared over n2 type idea. Now, under H0 though, right, under the null hypothesis, theta A is equal to theta B. So we could write that as just a single theta then. No need to estimate them separate under the null hypothesis. So therefore, if I substitute theta in the equation above for both theta A and theta B, I can then factor that out, and I get theta 1 minus theta times 1 over NA plus 1 over NB. This is very similar to the theta 1 minus theta representing SP squared kind of idea. Okay? So similar idea. We do need an estimate for theta, though. We don't have an estimate. all we've done under the null hypothesis is that they're equal. So our estimate will be a pooled estimate, much like the pooled variance estimate. So it's just going to be simply the number from A plus the number from B defective divided by the two ends. Okay? All right, so the standard deviation then becomes, we're going to use this, call this p hat, so p hat 1 minus p hat with the same quantity. Okay? So our test statistic then becomes, finally, the difference in the two means minus 0, or difference, I'm sorry, in the two proportions minus 0, which is similar to the difference in two means minus 0. Okay, y bar A and y bar B. All right, so same idea. Divided by some estimate of standard deviation, and again, you can see how that estimate looks similar to what's going on in a two-sample t-test as well. Now this will be a z-statistic from the large sample. Critical region, okay, we're doing a not equal to, so it's going to be absolute value of the test statistic bigger than z of alpha over 2, okay, because we're going to split it because it could be on either side. We're going to put alpha over 2 on the right, alpha over 2 on the left, where z alpha over 2 is the appropriate value from the z table, and a z of 0.025 now, okay, is 1.96. So our critical region is less than greater than absolute value of a test statistic greater than 1.96. Alternatively, most software programs, as we mentioned plenty of the other slides as well, will calculate the p-value. The p-value again is the probability from a z table now instead of a t will exceed the absolute value of the test statistic and multiplied by 2. Okay? So 2 times the probability z is greater than the absolute value. All right, so conduct the experiment. And, well, we have our numbers, right? We have 4% from A and 8% from B. Notice that, again, with equal sample size, then that p hat estimate is really just the average of those two. So that'll be 6%. And so we plug all those numbers in and we get minus 1.68. So recall that the critical region was the absolute value of that test statistic larger than 1.96. Also, we could take the 1.68 and go in and find the p-value. That gives a p-value of 0.09. So, since z absolute value of 1.68 is not greater than 1.96, or the p-value equal to 0.092 is not less than 0.05, we would fail to reject. So therefore, there is not sufficient evidence to show that the true proportion of defects differs between the two plants. Even though we had double the amount of defects in B, we did not have enough evidence to statistically say that they were different. Now, we could also use a confidence interval. We could calculate confidence intervals for both theta or theta A minus theta B. Okay, I didn't present that, but we could do it for both individual one proportion tests and two proportion tests. These confidence intervals can be used to provide a range of plausible values for the true parameter, much like they can for a single mean or a difference in means. In addition, recall, we can always use the confidence interval to test the null hypothesis by simply checking, is the null value, or target value or null value, inside the confidence